It's online.
Thank you, Richard. Hello, everyone. Welcome to the seminar of the Astronomy Department of our institute, University of São Paulo. Thank you all for your participation. And today we have the pleasure of having the presence of Dr. Mehrnoosh Tahani from Dominion Radio Astrophysical Observatory in Canada. Dr. Mehrnoosh, thank you for accepting this invitation. Mehrnoosh completed her undergrad studies in Iran, and she got her PhD in 2019 from the University of Calgary in Canada. Currently, she's a research associate with a Covington postdoctoral fellow at the Dominion Radio Astrophysical Observatory. Soon she will join, this year in September, right, Mehrnoosh, she will join the Stanford University in the US to work as a postdoctoral researcher. Some of the Mehrnoosh areas of interest are magnetic fields, molecular clouds, star formation, Faraday rotation, dust polarization, Magnetohydrodynamic Simulations, interstellar medium, radio astronomy, and some other topics. Today she will talk about novel techniques for determining the 3D magnetic fields of interstellar clouds. Questions can be asked to Mehrnoosh after her presentation. And if you are following the seminar via the YouTube channel, you can write down your questions in the chat, and I'll bring it to Mehrnoosh at the end of the presentation. So I wish a good talk to everyone. Mehrnoosh, feel free to start. Please.
Thank you very much. Thank you so much for the kind introduction and for the invitation as well. So I'll just go ahead and share my screen. So I'd like to start by acknowledging my collaborators who I have listed their names here, who have contributed to some of the projects that I will mention and talk about today. And I'd like to particularly acknowledge undergraduate students who have made contributions to this research. So today I'll be discussing the 3D magnetic fields associated with molecular clouds and how we observe them. So our path or journey was started by a new method that we developed based on Faraday rotation to detect the line of sight component of magnetic fields in molecular clouds. So first I'll give a brief introduction and motivation, and then I'll talk about the technique, the line of sight technique and the results that we got from the technique, and then I'll talk about different projects that we carried out to reconstruct the complete 3D magnetic fields associated with molecular clouds. And then if there is enough time at the end, I'll talk about some of the exciting and upcoming observations that enable us to explore the role of magnetic fields in star formation. So just a recap, I think most of people are familiar, but a quick recap that we know star formation starts in molecular clouds, and molecular clouds are known to be the nurseries for star formation. And Herschel, different observations, including Herschel observations, showed that it's actually dense filamentary structures, as you can see with the yellowish color here, that are the nurseries for star formation. So stars actually form within these dense, narrowed filamentary structure. So if we take a homogeneous cloud, for example, as we saw at the beginning in this simulation, and we perturb the cloud starts evolving, and it forms these dense filamentary structures. And then these dense filaments, they themselves gravitationally collapse and form cores and stars. So gravity is obviously an important parameter in the star formation story, but it's not the entire story. There are other parameters such as magnetic fields that influence these processes. So to be able to understand how magnetic fields influence this process, we need to observe their 3D structures. Just an example of these influences of magnetic fields, we now know that magnetic fields can inhibit the gravitational collapse and allow for formation of denser structures. So let's see how we can observe their 3D structure. The observations of magnetic fields in the interstellar medium was started by Hiltner and Hall in an attempt to detect starlight polarization. So in 1949, Hall looked at his observations and found that the polarization that they were thinking is actually caused by the starlight is due to the interstellar medium. And very quickly, Hall, using his observations, confirmed Hiltner's hypothesis and said, yes, the polarization that we are seeing is actually due to interstellar medium. And then again, very quickly, Davis and Greenstein attributed this polarization to the alignment of dust particles in the interstellar medium to or with galactic magnetic fields, and Spitzer and Taki associated this with ferromagnetic characteristics of dust grains. So we've come a long way since then, and there are various techniques to detect and observe the magnetic fields in the interstellar medium. These techniques include Faraday rotation, dust and starlight polarization, and Zeeman measurements, among others. Faraday rotation provides the line of sight component of magnetic field, so the component that is pointing toward us or away from us, and it has been used to detect the magnetic field in large galactic structures. As for example, we can see here in the study by Van Eck et al., which used the very large array observations to study the large-scale galactic magnetic fields. In addition to this, it has also been used to study the magnetic fields of highly ionized regions, and it was previously never used for molecular clouds, but we're interested in molecular clouds. For molecular clouds, dust polarization, starlight polarization, and Zeeman measurements have been successful to map the magnetic fields in these regions. Dust and starlight polarization provide the plane of sky component of magnetic field, so the component that is parallel to the plane of sky or perpendicular to the line of sight. As we can see with the black lines here, I'm not sure if it's really or easily visible here. So these black lines are observed here in this study by starlight polarization. Dust polarization also provides the same magnetic field orientation, but these two techniques do not provide the direction of magnetic field. Zeeman measurements provide the line of sight component of magnetic field, but because they require long telescope integration hours, there are not enough Zeeman measurements or line of sight magnetic fields per molecular clouds available. So we developed a new technique, maybe it's not new anymore, in 2018, based on Faraday rotation to detect the line of sight component of magnetic fields in molecular cloud. So again, a quick recap on Faraday rotation. When a linearly polarized electromagnetic wave passes through a region that is magnetized and has free electrons, its plane of polarization rotates, and the amount of rotation, or delta psi, is given by this formula, where lambda is the wavelength of the electromagnetic wave, B is the magnetic field in the region, Ne is the electron volume density, and dl is the path length. So the quantity in parentheses is known as rotation measure. So if we have information about rotation measure, we can find the magnetic field in the region. So now to use this in our method, we use extragalactic sources or rotation measure point sources. These are typically radio galaxies or quasars that produce a linearly polarized electromagnetic wave. And the medium that provides a region that is magnetized and has free electrons is our own galaxy. So as the linearly polarized electromagnetic wave from these point sources passes through the galaxy, their plane of polarization rotates. And so by observing different wavelengths or by observing the polarization angle at different wavelengths, in a traditional case or sense of rotation measure, we can find the rotation measure by using the linear relationship between lambda square and delta psi, or the amount of rotation. So now to use this for molecular clouds, we have to answer two questions. The first question is, how do we decouple the galactic contribution, or the contribution from everything else along the line of sight, from the contribution of the molecular cloud, because we are interested to find the rotation measure of the cloud itself. And then after we find the rotation measure of the cloud, the second question we have to answer is, how do we find the magnetic field, how do we find the electron volume density and the path length to be able to find the magnetic field? So we answer the first question by using an on-off approach. So in this approach, we divide the integral into two parts: the contribution from the molecular cloud, and then the contribution from everything else, or the galactic contribution. The galactic contribution comes from rotation measure point sources that fall near the cloud, but are far enough away from it that are not really associated with the cloud. So they don't really probe the magnetic field of the cloud, but they give us information about the galactic contribution. And we take a number of off positions. So we refer to these points as off positions, and the rotation measure as rotation measure off. And then the on position, or the position that give us information about the magnetic field, come from the rotation measure points that fall near the cloud or on the cloud. So they're probing the magnetic fields of the cloud and its surrounding. So by using Rm on minus Rm off, we can find the magnetic field of the molecular cloud. And in this approach, we use the rotation measure catalog of Taylor et al. 2009. And with this, we've answered the first question. So we know the rotation measure of the molecular cloud now. To answer the second question, we simplify the integral a bit further. We assume that the line of sight component of magnetic field is roughly constant. So what we are left with now is the electron column density. So instead of finding electron volume density and the path length, we need to find the electron column density. And for that, we use Extinction Maps and chemical evolution code. So any extinction map or even hydrogen column density maps can be used, and any chemical evolution code can be used. And for this, we use extinction maps provided by Kainulainen et al. 2009 and a chemical evolution code developed by René Plume at the University of Calgary. So we have these three tools. Let's see how we answer the second question and find the electron column density. I'll get into some details here, but that's because we are upgrading the technique. So I would love to hear comments and questions from you. So that's why I'm providing a bit more details. Using extinction maps, we get an extinction map of the region. Then if we plot rotation measure points, they look like something like this. Rotation measure positive is shown with blue, negative is shown with red. Positive on average means, in the convention of rotation measure, means that magnetic field on average is toward us, and negative means that on average magnetic field away from us. And if for simplicity we just take one or consider one rotation measure point and follow one rotation measure point on the map, from the map, we have its extinction value, and therefore using a conversion factor, we have the hydrogen column density value associated with that rotation point. At the same time, we simulate the chemistry of the cloud. So for each cloud, this is different. And as input parameters, we take temperature of the cloud, density, and most importantly, cosmic ionization rate and UV ionization rate. So for each cloud, this is different. And as output, we get abundance of elements versus extinction. And one of these elements is electrons. So we have now, based on the extinction value of the map, the abundance of electron. And then based on the hydrogen column density, we have the electron column density. And with that, we've answered the second question. First question, we had the rotation measure of the molecular cloud. Now we have the electron column density of the cloud, and we can determine the magnetic fields in the region. So blue shows magnetic field toward us, and red shows magnetic field away from us in the cloud. So I've actually skipped some of the details, but for like all the details are included in the paper, and I'll be happy to answer any questions you might have. So now we mapped the magnetic fields in 4 clouds or 4 molecular clouds of Orion A, Orion B, Perseus, and California regions to examine the method. And what we found was that whenever we had nearby molecular Zeeman measurements, our results were consistent with molecular Zeeman measurements. And in terms of comparing with atomic Zeeman measurements, whenever we had atomic Zeeman measurements, our results were consistent with atomic Zeeman measurements in terms of direction. For molecular Zeeman measurements, our results were consistent both in terms of direction and strength, because we're essentially comparing mostly molecular regions. One thing I forgot here. So this map here shows the California molecular cloud. Blue shows magnetic field toward us, and red shows magnetic field away from us. And when we look a bit more carefully, we see that at one side of this filamentary structure, the magnetic fields are predominantly pointing toward us, and at the other side, the magnetic fields are predominantly pointing away from us. So there is a reversal from one side to the other. We also see this reversal in the Orion A cloud, and in the Orion A, this was previously observed using atomic Zeeman measurements with the same direction that we detect. And also the strength is also relatively comparable in terms of from one side to the other. So this reversal, we also see it in the Perseus molecular cloud. In the Orion B cloud, we did not have enough data points to confirm or refute presence of a reversal across the cloud. So the code that I developed for this technique was recently updated by my undergraduate co-op student at the Dominion Radio Astrophysical Observatory, who is an undergraduate student at the University of Victoria, and is available and public on GitHub. So far of the talk, we talked about the technique, and one thing I'd like you to remember is that we developed a new technique to probe the line of sight component of magnetic fields, and in some clouds we saw that this component reverses from one side of the cloud to the other. So next, we want to use these line of sight observations to reconstruct the 3D magnetic field morphologies. So the first step that we took was using dust polarization observations, or particularly here dust emission polarization observations, to construct 3D magnetic field morphologies. So 3 magnetic field morphologies that can explain this reversal are toroidal, where magnetic fields form toroids around the filamentary structure; helical, where they form a helix around the filamentary structure; or arc-shaped magnetic field morphology, or bow-shaped morphology. In the arc-shaped morphology, regardless of how the filamentary structure is formed, the environment is thought to be interacting with the field lines and bending them around the filamentary structure. So in terms of Orion Eridanus, in terms of Orion A region, this responsible environment can be Orion Eridanus superbubble. So we used our line of sight and Planck dust polarization observations to explore these morphologies. So we constructed models representing each of these morphologies, and we obtained synthetic observations from models and compared them with the observations of line of sight and plane of sky magnetic fields. And using a series of Monte Carlo analysis, investigating a range of systematic biases between the two techniques that probe the magnetic fields and chi-squared probability values, we concluded that for the Orion A region that I'm showing here, an arc-shaped magnetic field morphology is the most probable candidate to explain this reversal. So this arc-shaped magnetic field morphology, we just know it's an arc shape. We didn't determine its orientation, whether it's concave or convex from our point of view, or its direction. So we then used another technique, combining our line of sight and plane of sky observations with galactic magnetic fields to reconstruct, this time, the complete 3D magnetic field morphologies in molecular clouds. So here I'm showing the Orion A region. The drapery lines show the plane of sky magnetic fields as observed by Planck, dust polarization emission by Planck, and the red lines just trace these lines for visual purposes, and the dots show line of sight and plane of sky, line of sight magnetic field toward us and away from us. So we use the galactic magnetic field model of Janssen and Farr 2012, and with my NRC co-op students, Jennifer Glover and Wednesday Lupipchu, we reconstructed the complete 3D magnetic field morphology of two clouds, the Perseus cloud and the Orion A cloud, and these are currently published and available. So co-op students who contributed are Wednesday Lupipchu, who's a co-op student at the Dominion Radio Astrophysical Observatory and is an undergraduate student at the University of Calgary, and Jennifer Glover, who I previously mentioned. So for the Perseus cloud here, the drapery lines show the plane of sky magnetic fields observed by Planck. The circles show magnetic field, the line of sight component of them, and using these components along with galactic magnetic fields, we reconstructed the complete 3D morphology and found it to be an arc shape, concave from our point of view, and it points in the decreasing direction of the galactic longitude. So now we have the full direction and orientation of this arc shape for the Perseus cloud. And one thing I should mention is that this arc-shape morphology is approximate and large scale. So we are ignoring the small scale fluctuations as a result of substructures forming within the cloud. Then using this 3D magnetic field observations, we can compare them with the cloud formation models that predict the 3D magnetic field morphologies. So one of these cloud formation models is the cloud formation model of Inutsuka et al. 2015, where a multi-compression scenario is needed to explain the formation of dense filamentary structures by expanding bubbles, which are typically generated by supernovae. And this cloud formation model actually predicts the bending of a magnetic field around the formed dense filamentary structure. So in a simplified case, if we consider a dense cloud somehow formed on the shells of these bubbles is moving with the velocity v toward a shock front, probably produced by another bubble, and if we have the initial magnetic field in the region that has a component that is perpendicular to the propagation direction, then this results into the bending of magnetic field around the formed filament. And this is also seen in ideal magnetohydrodynamic simulations by Inoue et al. 2018, where if we consider a dense cloud with the particle density of 1,000 per centimeter cube and a sheet-like shock front or H1 gas with the particle density of 100 per centimeter cube, and this dense gas collides or interacts with this shock front, then as a result of that, we have filamentary structure formed, and the magnetic fields actually bend around the formed filamentary structure. And this bend magnetic fields actually allow for accumulation of more mass onto this or like valley-like magnetic field and onto the filament, and allows for formation of denser filaments. So using these, we can make predictions for the line of sight and 3D magnetic fields of clouds that we are observing. So if we, for example, have our dense cloud that is moving with the velocity v in the H1 shock front co-moving frame, and if the initial magnetic field is has a component that is perpendicular to this velocity and points down to the page here, Then this results in a concave magnetic field, and therefore results in magnetic field away from us on this side and toward us on this side. The opposite is true. So if we have the velocity direction in the opposite and magnetic field has the same direction, then this would result in a convex magnetic field morphology and magnetic fields toward us and away from us in the opposite orientation. So now to use this, we decided to assume that the initial magnetic field in these regions can be approximated by the galactic magnetic field models. And for velocity observations, we use the velocity observations of CO from the Tom Dame survey and the H1 observations of High 4-pi survey. And we assume that the cloud retains a memory of the most recent interaction that it has gone through. So using this, we can find the velocity of CO in the H1 frame of the Perseus cloud, and we found it to be pointing away from us. And we modeled the galactic magnetic field, which is shown in this with the red vector here. Using the Janssen-Ferrar 2012 model. So the galactic magnetic field is the same orientation as Planck observations, and the velocity, since it's pointing away from us, this would result in a concave magnetic field morphology and magnetic fields away from us on this side and toward us on this side, which is exactly consistent with our line of sight magnetic field observations and our 3D magnetic field observations. So then using these, we can actually provide a step-by-step scenario for the formation of this arc-shaped magnetic field morphology for the Perseus cloud. So previous studies, for example, the study by Bialy et al. 2021, identified a large bubble in this region that has likely formed or contributed to the formation of the Perseus cloud. And they, using 3D dust maps, they identified or they determined that the Perseus cloud is located behind this bubble. So the sun is located here, and the Perseus and the Taurus molecular clouds are located on the edge of these bubbles. So so in the step-by-step approach that we identified or determined or proposed for the formation of this arc-shaped magnetic field morphology, first we need an initial magnetic field, which is our galactic magnetic field. This initial magnetic field is then bent in a large scale by interaction or recurrent interaction by bubbles such as per tau bubble. And this has resulted in a large-scale magnetic field bending that is not really observable in line-of-sight observation. So we can't really observe a line-of-sight reversal for this large-scale bending. Then we propose that there must be another bubble that has contributed to the formation of this arc-shaped magnetic field morphology. So we propose that there must be a structure or a shock front that has pushed actually the H1 gas around the filamentary structure formed on the per tau bubble and has resulted in a sharper magnetic field bending that is exactly associated with the 3D magnetic field structure that we reconstructed for the Perseus cloud. So now we can observe the line-of-sight observation or line-of-sight magnetic field data for this morphology. So we looked into the data, including H1 maps or thermal dust emission, H alpha and other maps to see whether we see an evidence of this bubble. And we do see evidence of, or some suggestion of this bubble using the 3D and thermal dust maps as well as H1 maps. But we're not really confirming that there is a bubble behind. There must be something that has interacted with the region, but we don't know yet. That is for other observations to determine the presence or confirm the presence of a bubble-like structure here. So we did the same thing for the Orion A cloud. For the Orion A cloud, because the magnetic field, so the galactic magnetic field looks along the filament and not perpendicular to it when it's projected onto the plane of sky. Not in 3D, only when it's projected onto the plane of sky. And the filament also has an inclination, then the scenario becomes more complex. But then using plane of sky and line of sight and galactic magnetic fields, we were still able to reconstruct an approximate 3D magnetic field morphology for the Orion A cloud and compare them with the cloud formation model predictions of Inotsuka et al. 2015 and Inoue et al. 2018, and we found it to be consistent. And for the Orion A, we provide a similar step-by-step cloud formation model again. So now we've reconstructed the complete 3D magnetic field morphologies. We decided to look into magnetohydrodynamic simulations and to see whether they are consistent with our observations when we take an isolated filament. So the filament is not really interacting with the environment. So for this, we use Flash, which is a high-performance, publicly available multi-physics, multi-scale simulation code. And we simulated an isothermal cylinder or isolated cylinder with a plumber-like density profile. And we explored a wide range of parameter space, including different orientation of magnetic fields and different velocities in the region, or different densities in the region, or different like turbulence component. And one of the components that we introduced to these simulations were rotating the filaments and actually like the box, like each separately, to see whether like there is any chance to or like constructing helical magnetic fields. And in none of the simulations, helical magnetic fields were generated. So this was another confirmation of arc-shaped magnetic field morphologies. And then with undergraduate student co-supervised by Ken Chen at the National Taiwan University, whose name is Xinyu Chen, we decided to introduce interaction with the environment, so velocity information, and we introduced again a wide range of parameters by these new parameters in the simulation, and we were able to find arc-shaped magnetic field morphologies. So far, I'll give a quick summary of what we've discussed. We developed a new technique based on Faraday rotation to detect the line of sight component of magnetic fields in molecular clouds. Prior to our technique, it was thought that Faraday rotation cannot be used for molecular clouds. And we saw that for some clouds, the line of sight component of magnetic field reverses from one side to the other. And then using our line of sight and Planck's plane of sky magnetic field observations, we reconstructed or concluded that arc-shaped magnetic field morphology for the Orion cloud was the most probable one. excuse me. And then we reconstructed the complete 3D magnetic field morphology of the Orion A and Perseus cloud using plane of sky, line of sight, and galactic magnetic field observations, and compared them with cloud formation model predictions, and found them consistent with these predictions of Inutsuka et al. 2015 model. But this is a sample of only 2 clouds. And these clouds are located in a relatively simple environment within our own galaxy. We need a large sample of clouds to be able to compare them with a large number of cloud formation models and better understand how these clouds are formed, and use the 3D magnetic fields that we observe in simulations to see how they influence the evolution of these clouds and formation of substructures and cores and stars. So for that, we need to observe the line of sight magnetic fields of many more molecular clouds. We then need to determine the 3D magnetic field morphology of many more clouds and compare them with cloud formation models, so we can understand whether magnetic fields are acting as an enemy, friend, or frenemy for star formation. So that is possible with new and upcoming observations. Previously, for line of sight magnetic field observations, we used the synthesis telescope at the Dominion Radio Astrophysical Observatory or the Very Large Array in New Mexico. But with the upcoming or new observations by the SKA or the Australian Square Kilometre Array Pathfinder, particularly the POSSUM survey with ASCAP, we will be able to map the line of sight component of magnetic fields in many more molecular clouds, and we'll be able to actually determine the line of sight component of magnetic fields in these clouds with much more details and better understand their substructures as well. And to reconstruct the 3D magnetic fields, we also need the plane of sky observations with better resolutions than what Planck could provide and better sensitivity. And for that, we plan to use the Fred Young submillimeter telescope in the CCAT Prime collaboration within the Galactic Polarization Working Group led by Laura Fissel. And with that, I'll just, so that's the end of my talk, and I'll just leave my summary slide. Thank you very much for your time.
Thank you a lot, Mehrnoosh. It was a very interesting and easy to follow talk. And I found it very smart, the models you built, and I was very curious in the first images you showed the measurements of the Faraday rotation, why the magnetic fields in the line of sight, more or less in the middle of these clouds, they were less intense than in the other parts. Now it was very clear, and I think it's a very clever way to model this problem.
Yeah, one thing I'll mention, sorry, that's actually a really good observation. For example, for the Orion A cloud, we find that at one side, the magnetic fields are twice smaller than the other side, and this is confirmed with the Zeeman atomic Zeeman observations. And we actually can explain it by the cloud formation scenario that we use for these clouds.
Yeah. I will open now for the questions. I myself have some questions, but Betty is the first here.
Thank you.
Oh, Betty, please, you can make your question.
Hi, interesting talk, thanks.
Thank you.
I have a couple of questions, actually. When you use the technique based on and off, you need, in the off position, to have a nearly empty sky, right?
Exactly.
But there might be some structures over there, like clouds, molecular clouds or smaller structures, molecular cloud structures, or even, smaller clouds. How do you deal with this? How can you clean the map and decide, okay, this is the off configuration, a reliable off configuration for the background?
That's an excellent question. So we tackled this issue by using different approaches. One is using a number of off positions at different locations surrounding the cloud. And we take different criteria for the off positions. One of the main criteria is lowest extinction values. So we pick points that have the lowest extinction values for to be able to subtract the off positions. And we make sure that we sample like the entire region around the cloud. So that one of the main things that we rely on. And for these clouds particularly, we are somewhat lucky because they are located in relatively high latitude regions. And they are also probing the anti-galactic direction. So there are less contamination. And we also use 3D dust maps for better modeling for these off positions. There's a lot of details taken into account for these off positions. We not only take an entire region of the cloud, but we also determine the magnetic fields by taking one region that shows magnetic field toward us, and off position only for that region, and then off position only for the region that shows magnetic field toward us or away from us, like these two components separately. So these are the main things that we take into account, but we are also for the on positions for the magnetic field of that we are probing with the on positions. We also rely on dust maps, but we also rely on the fact that we have a number of magnetic field values. And it's not only located within one region. And we estimate an uncertainty range. Our uncertainty range is relatively high because of all these factors of subtracting rotation measure values. But we are right now updating the technique even further using different algorithms, including machine learning. This area is one of the main areas that we're particularly focusing on to make sure that we can apply this technique for any cloud, not only these clouds that have relatively easy environments.
Right. Yes, interesting. And if I may, can I ask you, are you, because you mentioned comparisons with the Zeeman effect observations, but there are currently other techniques to build the three-dimensional structure of interstellar magnetic fields, particularly in molecular clouds. Are you familiar with this method based on velocity gradients, this technique developed by Lazarian and collaborators?
Yeah, absolutely. Those are great techniques to complement the determination of 3D magnetic field.
Did you have the chance to make quantitative comparisons, for instance, with this method?
So So far, no. I believe we have looked at different regions right now, but yeah, velocity gradients are powerful for probing the plane of sky magnetic fields, and then as you mentioned, and then using the recent techniques that they've developed by Hu and Lazarian, and Shu, I believe, as you mentioned. By using polarization fraction, they can probe the 3D magnetic fields, but actually, so by using polarization fraction, they can provide the inclination angle. But this inclination angle gives us a degeneracy. I don't think they have discussed it in their paper, but it cannot give us the 3D magnetic field morphology because we don't know the plane of sky magnetic field direction. We know the orientation, but not the direction. So there is a degeneracy. I've submitted a mini review and I've made a picture for that. I don't have it right now to show, but there is a degeneracy and it doesn't really provide the complete 3D magnetic field. But if we use that technique along with the techniques that I mentioned today, then we'll be able to determine the 3D magnetic fields with a lot more detail, finer detail, and more precision. So that's one of my plans to actually use these two combinations. Also, I shall mention the study of Chen et al. 2019 looks at these as well. But yeah, that's an awesome question.
Right. If I may, can I make another question? Because you probably have seen the recent observations by Meerkat of all the bubbles, all the supernova remnant bubbles.
I lost your voice.
Sorry. I have a third question, if I may. Wow.
Sorry, I may some people from outside the university. I allowed them to enter, but we had some problems. You can continue, please.
Oh. You probably have seen this recent observation by Meerkat with the supernova remnant bubbles spread all over the galactic plane. Did you have the chance to compare, because your results for the two clouds and this complex structure that may suggest that you have the progenitor are the bubbles, one or more bubbles. Did you have the chance to compare with, for instance, these high-resolution radio maps by Meerkat, and to see whether this correlates, for instance, the region that you are studying correlates with structure?
Yeah, that's another excellent question. I have not had the chance yet to make the comparison, but as we are observing more and more line of sight magnetic field observations and 3D, I'll be definitely looking into comparison with Meerkat observations, which are actually really beautiful, and look at the structures of bubbles around these regions when inferring their 3D magnetic field structure.
Okay, thanks, and again, very nice talk. Thanks.
Thank you very much.
You're welcome.
Thank you, Betty. Now, Maria will make a question. Because we had some problems with people from outside the university, from now I'm allowing only people with the university email to enter in this call. Maria, please.
Yes. Can you hear me?
Yes, yeah. I'll stop sharing for now.
Okay, yeah. So I was wondering, nice talk, very nice talk, by the way. And I was thinking about, you mentioned you wanted to explore and to test more, let's say, the technique observing much more clouds, a number of clouds. I guess there are some parameters that these clouds should have. How special these clouds should be? What are your sensitivity limits? Do you need a special diameter, let's say, or size in the sky? And if you have a look into this, like how many of the clouds that we know actually can be in this category?
That's a great question. Thank you. So that actually depends mostly on what rotation measure catalog we use. Previously, with the rotation measure catalog of Taylor et al. 2009, because the observations were initially not for the purpose of rotation measure, they did not have enough observing band. So the uncertainties in the rotation measure catalog is relatively high. And then there are sometimes when we get close to the disk, we can't really be 100% sure that this rotation measure is absolutely correct, and there is no wrapping of the n pi rotation measure. If you are using the Taylor 2009 catalog, then we are limited to looking at clouds that are high latitude, so like higher than 10 latitude degree, or like lower than -10. And but with new and upcoming observations by rotation measure, by VLA All-Sky Survey or POSSUM survey that are becoming available within these collaborations, then we'll be able to expand the regions that we can actually probe, because they not only the uncertainty is significantly reduced by a factor of 10 or more, but they also provide a source density that is significantly increased. So for example, Taylor et al. Had a source density of 3 rotation measure per square degree, but POSSUM, for example, has 30, like a factor of 10 rotation measure per square degree. And so like these enable us to probe the off positions and the on positions better, and with this we'll be able to map the line of sight magnetic fields that are like closer to the disk as well, at least like above 2 degree, and we can also explore regions that are anti-galactic center with 3D dust maps as well. So with the increased sensitivity and resolution and source density, we will be able to look at a much larger region. Still, looking at the disk would be tricky, but there are some clouds in the disk that are very bright, for example NGC 6334. So if we have a cloud in the disk that is very bright, we still be able to probe their line of sight, and then consequently the 3D magnetic field morphology of them.
Okay, I understand. I had another question, but I forgot. Sorry.
Oh, sorry.
So I would let Reinaldo, and I will think about what it was. I'm really sorry.
Okay. So I'm curious about the chemical codes used to obtain the electron density, volumetric density. So does it introduce new parameters to the problem? Because I don't know if you have to put by yourself the chemical abundances in the clouds. Does it introduce some uncertainties?
Yeah, it does. Yeah, that's another excellent question. So when we determine the uncertainties of line of sight magnetic field observations, we explore a wide range of parameters that can contribute to these uncertainties. Rotation measure points, off and on positions, and then the chemical code. So with the chemical code, for each of these parameters, the density, the ionization rate, and the temperature, we explore, like we say that, let's see if we change the density by 50%. And see how much the results changes in the chemical code, and then finally in the magnetic field observations. And let's change temperature by, I believe we change the temperature by 20 or 30%, and see the upper and lower values of magnetic field for that point that we get. So with this, we calculated the uncertainty range, and we have relatively large uncertainties, but it's actually surprising because the with the chemical code and obtaining the magnetic fields at the end, the main contribution of the uncertainty is the uncertainties of the rotation measure data themselves, because the Taylor catalog had a large uncertainty, and then what we get from the subtracting the off positions. So the uncertainties from the code was relatively small, like smaller compared to the like this subtracting off positions.
Right. And did you find some significant correlation between the values of the electron density and the intensity of the magnetic field, at least the components along the line of sight?
I'm not sure I understood the question. Are there any correlation between?
Yeah, did you find some correlation between this, the electron density and the magnetic field intensity? At least these components along the line of sight.
Yeah. So that's maybe I'll quickly share the screen while I'm like answering this question. So for each cloud, we're probing like the regions that are less dense and regions that are like denser. So obviously, as the result, like the electron column density and the electron abundances are different. So there are some points here that is actually not really visible because like they're very actually tiny, that fall on the regions that are very dense. And even though the electron density is higher and the density of the region is higher, and we expect to get magnetic field that is stronger, we ended up getting a magnetic field that is smaller. And that's actually because as we probe the line of sight magnetic field, we are dividing the cloud from the outer layer to like denser layer and again outer layer. And we're probing the average magnetic field along all of these. And then there is, as we get to denser regions, the magnetic field has a lot more fluctuations, and then it reverses sign and then reverses sign again. So it ends up producing depolarization, and we get smaller rotation measure and smaller magnetic field. So we do see some, when we go from like extreme lower density to extreme higher density, we do see some correlation, but it's actually the opposite correlation that
anti-correlation, yeah. I was about to ask if you, in your model, you have to put some parameter to give account for this depolarization. I don't know, maybe it's due to some random components.
Yeah, right now we cannot do that, but we're actually working on another technique by using Faraday rotation cubes to be able to do that. So with that, like instead of point sources, we have a like Faraday rotation space or Faraday depth data. So yeah, hopefully we'll be able to in the future.
Nice. Let's finish this discussion with the question by Maria.
Yes, I remember. Sorry. Because it actually was directly related to my question, my previous question. I was wondering if you if your code is really automatized to treat large amounts of data, meaning like if you have a big number of clouds, can you do this? Be sure that you are getting the correct answer, let's say, without having to tune each of the clouds.
Yeah, right now the code is semi-automatic. Like if you want to run the code without really thinking about the off positions, then it's fully automatic. Like it asks you whether the approach that it's doing is correct, and it pops up plots to show the off positions, the stability trends, and like the magnetic fields as the result of different off positions. But the number of off positions, it's not very reliable the way it's completely automated in the code right now. But we are working on like fully automating that part right now, and we'll like push any changes that we make on GitHub. So yeah, right now the way the code is, if you want to get reliable magnetic fields, it needs like parameter tuning from mostly for off positions from the user. But in the GitHub, we've also provided the chemical evolution output files, extinction maps or hydrogen column density maps of a series of clouds. So when you run the code, it asks you what cloud you want to explore. You can say like the name of the cloud, and if there is extinction maps available, then it starts running. But if the extinction map is not available, or the hydrogen column density map is not available, that also needs some coding from the user. But we're working on that.
This is really great, actually.
Thank you.
If there is,
yeah, hopefully we can update it much faster and better.
Thank you.
Thank you.
So before stopping the broadcast of this seminar, I would like to thank you again, Mehrnoosh, for this very interesting seminar and for sharing your new results and the new technique you're developing with your collaborators. Thank you again.
Thank you so much for the invitation. I really enjoyed talking with everyone.
Thank you. So let's end now the broadcast. So we can stop. Thank you. Okay, now.
Stop presenting.
Yeah. Yeah.